Okay, another video for the review packet solutions. So what we're going to do is, okay, let me just make this a little smaller. Okay, so what we'll do is we'll draw in an axis to work with. Hopefully we can use a straight edge. Okay, that'll be good enough, I think. So we're going to plot the points. 3, 4, 5, 6. And 1, 5. Okay, so we got CAT right there. Please use a straight edge. I can't on this, but really should. Okay. Let's see. We want to translate. This will tell us to move everything left 1, and that'll tell us to move everything down 6. So let's start with T, left 1, down 6. That should get us T prime, left 1, down 6. C prime, and A prime. Alright. Does it say state the coordinates? It says graph, which we did. Label is putting the points, the coordinates on there, or points, letters on there. Let's see, it doesn't say we have to state the coordinates. It wouldn't hurt to. Alright, now prove through coordinate geometry that those are congruent. Now the only way we can do that is either side, 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 or hypotenuse leg. Side, side, side's probably your best bet here. And what we need to do is just calculate the length of every side. Now we know what happened. We know that it's going to be congruent because we used a congruence, rigid motion transformation. But to use coordinate geometry to prove it, we really should calculate the length of each side. Okay? And sides with equal lengths will be congruent. So that's what we're going to do here. Okay, we got to actually just demonstrate that we're using either the distance formula or the Pythagorean theorem. All right, so we're going to go with lengths of sides here. Okay, AT is first. So what I have is a right triangle, 1 by 1, 2, 3, 4. So I'm going to say 1 squared plus 4 squared equals d squared for distance. That's going to give me 17. Square root of 17 ends up being AT. Okay? That's going to be its length. Now, unfortunately, we've got to go through the whole set. It's not going to be easy, but it's going to take a little while, but we can do it. All right, now AC. It's going to be 2 squared plus 2 squared equals d squared. That's 8. Square root both sides. So now AC is the square root of 8. Okay, keep rolling through here. And finally we'll go to TC. It's down 1 over 2. So we get the length of TC. It's going to be 1 squared plus 2 squared, which is 5. And that gets us TC. Okay, so that's all the sides of triangle CAT. Now we're going to go to triangle A prime, T prime. They're going to be identical, but just show that you're doing it. We know it's going to work out, but don't shortcut it. It's worth points. So let's just go through the process. Pretend like we don't even see this up here. Okay, basically we can copy it if you want. All right, so that you make sure it comes out the same. So A prime, T prime, whoops. A prime, T prime is square root of 17. Well, that's nice. They're the same. Surprise. A prime, C prime. Do the process. It's 2 squared plus 2 squared. All right, a prime c prime equals square root of 8. Okay, and finally ct, tc, t prime c prime. Okay, that one's going to be 1 squared plus 2 squared. And t prime c is square root of 5. All right, now we have to go through the process here, okay? And we got to start talking about it. So we're going to say AT is congruent to A prime T prime because they have equal lengths. Okay, 2. This seems crazy, but we got to do it. AC is congruent to A prime C prime. Again, because they have equal lengths. Okay, they're both square root of 8s. These are both square root of 17s. Okay, last one. TC congruent to T prime C prime. Again, for the third time, because they have equal lengths. Just, I know it's annoying, but just don't get lazy on me here. Okay, got to do it. They're both square root of 5. Done. Now, why are the triangles congruent? Now we get to say by side, 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 triangle congruence theorem. Okay, so there is one example of proof using coordinate geometry. All right, now we'll go through the other problems. Hopefully, go through a few more a lot quicker. What we got to do here, it looks like, is mark the diagram, and they want us to prove it by side angle side. Here's what I'm seeing. If you need to separate the diagrams, do that. Okay. Right here, they are showing that we have angle B in both. Now, we don't have to say it's a right angle. It looks like it, but we don't have to. There's a reflexive property, so that's our pair of angles. And if they tell us that DB is the same as BE, right, they're matching those. Now, what's missing? We got to have BC congruent to AB. That's going to get us, that's what's missing. That's going to get us the proof by side angle side. All right, so this one's silly because we don't need another pair of angles. So is that. AB, great. That's not even a choice. You got to be kidding me. Let's see. What did I mess up here? AB is congruent to BC. Is there an angle I'm missing? Okay. I don't see what I need here. Let's see. AD. Oh, okay. I am getting it now. All right. I figured it out. This part right here, sorry about that. If these are the same, okay, then AB is congruent to BC. All right. So that is going to end up getting us what we need. This is not going to do us any good. That's going to get us side-side angle. So this is what I wanted. I was looking for. It wasn't there, but now I see it. These pieces right here, what we can use is we can say, okay, now BE plus EC turns into BC. That was equal to BD plus AD. Okay, so that's going to work to get us AB. Okay, tricky, but I caught on to it. All right, line segment EA is the perpendicular bisector of ZT. Okay, so first perpendicular, then it bisects. Okay, which conclusion cannot be proven? EA bisects angle ZET. Well, it can eventually, because the triangles are going to be the same. So these will eventually be able to be the same. So let's hold off on that. We don't know. I think I can get to that. I'm pretty sure. Remember, it's which one's not. Triangle EZT is equilateral. I don't think I can prove that. Yeah, there's no reason. I bet it's going to be this one. EA is the median. We haven't taught you that yet, but it is. Angle Z is congruent to angle T. Again, the triangles are going to come congruent, so those are going to be the same. I like it. It's going to be, we cannot prove that the whole triangle is equilateral. Okay, let's keep going. Let's see. All right, this one's a classic here. Okay, this is going to get us side, side. I'm just going to mark them. All right, and we know that that doesn't cut it, right? Side, side doesn't cut it. Sufficient evidence means we need enough, and that's not enough. So let's throw that out. What we should know is these are all angles. Just angles is not enough. Okay, we need at least one pair of sides. This is going to get us angle, angle, angle. This is only getting us side, side. There's a sequence of ridge of motions that maps AB onto DE, BC onto EF. That would be pretty good if those are actually, in fact, matching. AB to DE, yes, BC to EF, and AC onto DF. That's going to be good. Okay? That should definitely be good. All right, this one's not quite going to cut it. Okay? Points mapping onto each other, I don't know. That might work. You know what? They didn't necessarily fix orientation. Let's draw it. Okay? So let's say that's ABC. What is it? DEF. Okay. So if we make sure point A hits point D, that's great. Okay, we can map onto that, right? AB onto DE. Angle B onto angle E. The whole angle. The only thing we aren't certain of is that location of C to F. So I'm not sure that we can get this one. All right, I am sure that that's going to do it. This might be enough, but this definitely is. So let's just use 3. We only got to give one right answer, so good enough. Two right triangles must be congruent if the lengths of the hypotenuse are equal, not quite. Corresponding legs are congruent, yeah, because that would get us, if we did that, okay, that would get us side angle side, so that's going to be good. All right. Let's draw a line of reflection. Okay. All right, if they're not telling me what to reflect over, let me just reflect over line BC. That'll make it easy. The only point that's going to then move, the only vertex, I should say, there's lots of points that'll move, but A would have to travel perpendicular and the same distance away. So let's assume that's A prime, and there it is. Okay, perpendicular and the same distance away, A prime, B prime, and C prime. Okay, next, translate triangle, sketch it. Okay, yeah, let's just write the notation. All right, let's try to estimate here. Let's try to keep it parallel and the same distance away. Parallel and the same distance away. Looks like that's C prime. Okay, write the notation of your translations. We're going to translate A to A prime. By that directed segment, we're going to translate triangle ABC, A to the directed segment A to A prime to get triangle A prime, B prime, C prime. Okay, C, rotate 180 about point C. That means A is just going to shoot straight through. So A prime's there. B should shoot straight through to get B prime there. C prime is invariant, so stays there. All right, good enough. And sketch after a point reflection in B, same thing. Okay, A is going to map to there-ish. C has to go straight through, same distance away, right about there. Close enough, I hope. Should be a straight path through, same with this. And it's also B prime. Okay, so that's the three that we're looking for. That's it for the review packet, and good luck on your test.